This is section 3.3, and we're finding real zeros of polynomials. First way we're going to do that is using the rational zeros theorem. It says the possible rational zeros of a polynomial are the factors of the constant divided by the factors of the leading coefficient. So in this example I have here, p of x equals x cubed minus 3x plus 2. The possible rational zeros, so there's going to be a rational number that is a zero of the polynomial. Those possible rational zeros are factors of the constant, which is 2, divided by factors of the leading coefficient, which is 1. So the possible rational numbers that are zeros of the polynomial are factors of 2, which are plus or minus 1 and plus or minus 2, divided by factors of 1, which are plus or minus 1. So that gives me possible numbers of positive or negative 1 and positive or negative 2, because when I divide 1 and 2 by 1, I just get themselves. So remember, a rational number is a number that can be written as a fraction. So there are potentially irrational numbers that are zeros of the polynomial. This theorem won't find those, but it will find the rational zeros. So these are the possible ones. I need to plug them in to see which ones are actually zeros. Now I can do that with synthetic division. So if I take 1, I can divide that into 1, 0, negative 3, and 2, and see if I get a remainder of 0. If I do, then it is a 0. I drop the 1, multiply, add, multiply, add, multiply, add. Hey, I got a remainder of 0. Therefore, 1 is a 0 of the polynomial. Once I have one of them, I can take this reduced equation, the one that I got as the quotient on my synthetic division, and I can just solve that. I don't need to go back to the original one, because if it's a solution to this reduced one, it's a solution to the original one. So this just says x squared plus x minus 2. That one's a lot easier to work with. Is that factorable? Are there two numbers that multiply to give me negative 2 but add to give me 1? How about positive 2 and negative 1? So that means I could factor the original polynomial that I had, x cubed minus 3x plus 2, as the x minus 1, which comes from the 1 that I divided by and found that was a solution, and another x minus 1 from down here, and x plus 2. In other words, x minus 1 squared times x plus 2. And so my zeros are 1 and negative 2, where 1 has a multiplicity of 2. So I've completely solved that polynomial and found all of its zeros. Let's do the same thing to this one so that I can be able to factor this polynomial, because the way it is, I don't know how to factor it. I could try factoring by grouping, but it's not going to work. So the possible rational zeros, to give me a list of numbers that I should try, I take factors of 6, so those are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and I divide them by factors of 2. Well, those are plus or minus 1 and plus or minus 2. So if I divide those numbers by these numbers, what numbers do I obtain? I obtain plus or minus 1. When I take 1 divided by 1, I can do 2 divided by 1 and get plus or minus 2. I can do 3 divided by 1 and get plus or minus 3. I can do 6 divided by 1 and do plus or minus 6. But I can also take all of those numbers and divide them by 2 and get plus or minus 1/2. When I do 2 divided by 2, I get the 1 that I already had. When I do 3 divided by 2, I get plus or minus 3/2. And when I do 6 divided by 2, I get the plus or minus 3 that I already had. That gives me 12 possible numbers to be rational zeros of this polynomial. I don't need to try all 12 of them. I just need to keep going until I find one that works. The easiest one to plug in is 1. Now I could use synthetic division, but 1 is a pretty easy number just to plug into the polynomial and see if it gives me 0. When I plug in 1, I'll have 1 cubed is 1 times 2 is 2, plus 1 is 3, minus 13 is 10, negative 10, plus 6 is negative 4. So that doesn't give me 0. So 1 doesn't work. So I can try negative 1. Negative 1 cubed is negative 1 times 2 is negative 2, plus 1 is negative 1, plus 13 is 12, plus 6, and that doesn't give me 0. Then I can try 2. And let's try dividing by 2 with synthetic division. It'll be 2, 1, negative 13, and 6. So drop the 2, multiply, add, multiply, add. And I don't get a remainder of 0. So 2 doesn't work either. Let's try negative 2. And I don't get a remainder of 0. So negative 2 doesn't work either. Let's try 3. And I don't get a remainder of 0. Let's try negative 3. There, I got a remainder of 0. So negative 3 works. Now I don't have to go back to the original one now. Now I work with this reduced equation of 2x squared minus 5x plus 2. So I'll just take that one, 2x squared minus 5x plus 2. I'll try to factor it and see if it factors. Well, I think it does. 2x minus 1 times x minus 2. So therefore, I can factor the original polynomial as 2x minus 1 times x minus 2 times x minus negative 3, which is x plus 3, since negative 3 was a 0. My goal was to factor the original polynomial, so I've done so there. Now let's find all the zeros of this polynomial. It's a 4th degree polynomial. It has 5 terms. No way I'd be able to factor that. So instead, I'll use the rational zeros theorem and find possible rational zeros. They're going to be factors of 10 divided by factors of the leading coefficient, which is 1. So just factors of 10, which are plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. So 8 possible numbers. Let's just start trying. Let's try the number 1. 1 to the 4th is 1, minus 5 is negative 1, minus 5 is negative 6, plus 23 is 17, plus 10 is 27. That doesn't work. Negative 1 gives me 1 plus 5, which is 5, minus 5, which is 0, plus 23 plus 10, or minus 23 plus 10 is negative 13. Doesn't work. Let's try 2, and I'll divide by 2. And I don't get a remainder of 0. 2 doesn't work. Let's try negative 2. And I do get a remainder of 0. So negative 2 works. Now I'll work with this equation, x cubed minus 7x squared plus 9x plus 5. That's still not in a place where I can factor it. I want to keep breaking it down until I get it to x squared. So I need to find another rational 0. Now, negative 2 was a rational 0, the original one. It worked. It could work again. It could be a multiplicity of 2. It could be a factor twice. So let's try negative 2 again and see if it works in this one, which has the coefficients 1, negative 7, 9, and 5. So I don't need to go back to the original coefficients anymore. And I don't get a remainder of 0. So negative 2 is only a factor once. Alright? If 1 and negative 1 didn't work, and 2 didn't work in the original one, it's not going to work in this one either. So let's move on to 5. Hey, that gives me a remainder of 0. 5 works. Alright. So now I have x squared minus 2x minus 1. That's a quadratic. That I can try to factor. But doesn't quite work. One of them would have to be positive and one of them would have to be negative in order to multiply to give me negative 1, but those don't add to be negative 2. So it doesn't factor. What do I do? Well, I can use the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So x is equal to 2 plus or minus radical 8 over 2, which is the same as 2 plus or minus 2 radical 2 over 2. I can cancel the 2 out of all of those and get x is equal to 1 plus or minus radical 2. So my goal is to find all the zeros. Here they are. The negative 2 that I originally found, and the 5 that I found, and now 1 plus radical 2 and 1 minus radical 2. So once you get it down to a quadratic equation, just use the quadratic formula to solve it if it can't be factored. Okay, another useful theorem is called Descartes' rule of signs, named after the French philosopher and mathematician René Descartes. It says the number of positive real zeros of a polynomial p of x is either equal to the number of variations of sign in p of x, or is less than that number by an even number. And the number of negative real zeros of p of x is either equal to the number of variations of sign in p of negative x, or is less than that by an even number. It's going to make more sense when you see an example. So let's find the numbers of possible positive and negative real zeros. So p of x equals 3x to the 6th plus 4x to the 5th plus 3x cubed minus x minus 3. So the number of possible positive real zeros is either the number of variations of sign in p of x or less than that by an even number. So I literally look at the equation and I count how many times it changes sign, how many times it changes from either positive to negative or negative to positive. So it starts out positive, stays positive, and then changes to negative, and then stays negative after that. But change sign once. So the number of possible positive real zeros is 1. The theorem says I can go less than that by an even number. But if I go, so that means go down by multiples of 2. If I go down by 2, I get to negative 1, and it wouldn't make sense for it to have negative 1 number of zeros. So I just go down until I get to a negative number. So I can't go down any further than 1 here. So there's 1 possible positive real zero. That means there is 1 real number that is positive, that is a zero of this polynomial. And only 1. Now the number of possible negative real zeros, I have to look at p of negative x. P of negative x is what I get when I plug in negative x for x. Now anywhere where there's an even power on x, the negative goes away. It doesn't do anything. So it's only going to change the terms that have an odd power of x. So p of negative x is going to be 3x to the 6th minus 4x to the 5th. That one changed sign because it had an odd power. Minus 3x to the 3rd, which had an odd power, so it changed. Plus x, because that has an odd power of 1. And then minus 3. Now I count the number of times this changes sign. Well, it started out as a positive 3 and then became a negative 4, so that changes once. Then it was a negative 3, so that's still negative. And then it changed from negative 3 to a positive 1, so that changed a second time. And then it changed from positive 1 to a negative 3, so that changed 3 times. So it either has 3 negative real zeros, or I can go down by multiples of 2 to get a number of negative real zeros. And if I go down by another multiple of 2, I'm at a negative number, so that doesn't make sense. So it has 3 or 1 negative real numbers that are zeros of the polynomial. Now, there could be complex numbers, imaginary numbers, that are zeros of the polynomial, and we'll get to that next time. So here, let's find all the zeros of p of x, where p of x is 2x to the 5th plus 5x to the 4th minus 8x cubed minus 14x squared plus 6x plus 9. Let's list out the possible rational zeros using the rational zeros theorem. Those are factors of 9 divided by factors of 2. So we'll have plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 1/2, plus or minus 3/2, and plus or minus 9/2. Let's just start with 1. If I plug in 1, I'll have 2 plus 5 is 7, minus 8 is negative 1, minus 14 is negative 15, plus 6 is negative 9, plus 9, and that's 0. So 1 works. Let's then divide by 1 with synthetic division to figure out the reduced equation that I can then work with. So now all I have to do is work with the equation 2x to the 4th plus 7x cubed minus x squared minus 15x minus 9. Now 1 could be another root, another 0. Let's see if it works again I have 2 plus 7, that's 9, minus 1 is 8, minus 15 is negative 23, minus 9. That doesn't give me 0. So then I can move on to negative 1. Negative 1 is also easy to just plug in. I'll have 2 minus 7 is negative 5, minus 1 is negative 6, plus 15. Negative 6 plus 15 is positive 9, minus 9 is 0. So negative 1 works. I'll divide by negative 1 to get the reduced equation to work with there. Now all I have to do is work with 2x cubed plus 5x squared minus 6x minus 9. Again, negative 1 could work again. Let's try it again. Negative 2 plus 5 is 3, plus 6 is 9 minus 9. That's 0. So negative 1 works again. So we'll divide by negative 1 again on this reduced equation. Now I have 2x squared plus 3x minus 9. That's a quadratic. Let's use the quadratic formula to finish solving this. I get negative 3 plus or minus 9 over 4. I can work that out. Negative 3 plus 9 is 6 divided by 4 is 3 over 2. Notice that was in my list of possible numbers. And negative 3 minus 9 is negative 12 over 4, which is negative 3, which is also in my list of possible numbers. So all of the zeros of this polynomial are the ones that worked when I divided by them. 1, negative 1, and negative 1 worked twice. I don't need to list it twice. But 1, negative 1, and then the ones I got from the quadratic formula, 3 halves and negative 3. Last one, we'll find all the zeros of this polynomial. This is a 5th degree equation, so we'll start with the rational zeros theorem. Let's find factors of 24 divided by factors of 1. Well, that's just going to be factors of 24 then. There are quite a few factors of 24. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. Let's start with 1, and we'll divide by 1 and see if it works. 1 gives me a remainder of 0, so 1 works. Now 1 could work again. So let's divide by 1 in the reduced equation that we have here and see if it works again. See if it's a double 0. And it does. It gives me a remainder of 0 again. So now I can divide by 1 again and see if it works a third time. No such luck. So 1 is a 0 twice, but we take that reduced equation that we got when we divided by 1 the second time, and we can just work with that one now. So I've got 1, negative 5, negative 2, 24. We can try negative 1 and see if negative 1 works. Nope, negative 1 doesn't work. So let's move on to 2. See if 2 works. Nope, 2 doesn't work. Let's try negative 2. Negative 2 does work. And it gives me this reduced equation, which is now x squared minus 7x plus 12. Because I had started with x to the 5th. When I divided by 1 the first time, I had x to the 4th. When I divided by 1 again, I had x to the 3rd. Now when I divide by negative 2, I have x squared. That is factorable. X minus 4 times x minus 3. So all of the zeros of this polynomial are 1, which worked twice, negative 2, 4, and 3. Does this make sense? Good.